So welcome to the pre-recording of lecture 34. So this is the second part of our 17th session at the end of week 6 of the 8-week summer course. So we have started the introduction to defining graphical user interfaces with Tkinter. So Tkinter belongs to the framework of Python. So what I want to enforce in this lecture mainly is the usefulness of object-oriented programming towards defining graphical user interfaces. Last time we introduced the canvas. We will see more applications of the canvas to draw things, and we will draw colors where we can control the color scale with scale widgets. In the second part of the slide presentation, I will start by introducing animations so we can make things that move. So I will animate a random walk. All right, so let's get started. So we can make colors by mixing the primary colors. So the three primary colors are red, green, blue, so 3 dimensions. 3 scales. What you see on the slide is the screenshot of a GUI that has one central object, which is the canvas widget, where one big rectangle is colored using the red, green, and blue intensities. So there is a red intensity of 81.2%, a green intensity of 41%, and a blue intensity of 26.2%. So these percentages are taken as values from the scales. With these three values, so there are floating point numbers, the hexadecimal representation of the color string is defined. So that happens internally in the GUI. So one canvas widget, several labels, and 3 scales, 2 vertical scales, 1 horizontal scale. So let's look at the code for one scale. So first of all, what do you do with the scale? You set the value of a variable. A scale is extremely useful to restrict the ranges of good values. So if you build an application with many parameters, it's rather cruel to ask the user for all kinds of values, and the user may have no clue, but you as a developer, you know what the good ranges are. So you can set also a default value. So you see at the bottom line, the set is a method that is defined on an object that is an instance of scale. That scale itself is a data attribute of our graphical user interface. So when we make a scale, we have to pass the window WDW. We have to set the orientation. So the red scale was a vertical scale. The length of the scale, the range, we will go from underscore, which is kind of quirky. We go from 0 to 1 with a resolution 1 over 256. Why that? Well, we use 1 byte, 8 bits, 2 to the power 8 is 256. So our floating point number will be a number that increases with increments of 256. So we can control a variable, but we can also launch a command. So we have a method and a data. So we have a data attributes associated to this. So this is this self.red, which is a double var. So a double var is an object representing a double precision float. The functional attribute, which is a method of this class, so the self.colors, that get executed whenever the user touches the scale. So three important statements in this constructor. I will show the complete code in the second half of this presentation. So we can enter. So here is a very basic scale, just only one widget. It actually doesn't do anything, but it shows a widget. It shows the definition of the orientation, horizontal scale. There is the meaningful range between 0 and 1, well, what is supposed to be meaningful in a particular application. And you can also show the ticks, and you can show the granularity. So here at the previous scales, you see that the granularity is actually 3 decimal places, but it will go up with this 1 over 256. So all the values that can be given, they are within a restricted range, but they also are values that for this typical application, they do have meaning. All right, so here is a more elaborate scale with feedback. Whenever the user presses the button, you will actually see the value displayed in the entry widget, but only when the button is pushed. The next, so this is the object-oriented version. The next GUI will actually be immediate. And that is the one that I will show the code for. Every GUI that we make follows a little bit the same template. We have a constructor, we pass the window, WDW. We have a method or many methods, but at least one method that defines the functionality, defines the actions, what happens if the user presses a button, touches a scale, etc. Here is the avoidance of a button. So try to, in the design of a GUI. So I made 3 attempts when I was developing this. So first a plain scale, then a scale with an entry widget and a button, but actually the button is superfluous. So here we have now only 2 widgets. And you can see what is displayed in the entry widget is the corresponding value. So this is to illustrate the whole sequence of actions that can happen now. So this GUI just displays the entry in the entry widget, the current value, but you could launch entire programs as soon as the user touches the scale. All right. How to make animation. So I will make an animation of a moving dot simulating a random walk. We introduced the canvas, and what was important there that in the canvas we work with the pixel coordinates. This GUI actually makes it even more explicit, and in some sense, but I didn't want to introduce these scales last time. So here you see that there are 2 scales, one on top of a canvas and the other one at the right of the canvas. With these scales, you can move the dot. And there is text that is displayed just above the dot. The text corresponds to the coordinates. And you see that the origin, contrary to what we typically might expect and we are used to, the origin actually is at the top left, not at the bottom left of the canvas. So the GUIs that are being made, so in some sense I will present in a Jupyter notebook a complete GUI. So in some sense pedagogically this is not entirely justified, but I hope you can also see that the GUIs are actually all kind of connected with respect to each other. I'm using this GUI a little bit as a modification of a GUI in the previous lecture, so in the first half of the session. I will use this GUI also as a stepping stone to the animation. So test early and often, execute early and often. is the guiding principle when we define Python programs. Whenever we define a GUI, we define the layout. So there are data attributes there. So the values that are controlled by the scale are actually also the data attributes that are managed by this GUI. So we have three widgets. So the widgets are determining the state of the GUI. And then so these are the data attributes of the GUI, of the object. So in some sense, when we were thinking about defining our own classes, we were thinking about making our own types, and we have many, many objects of that type. Object and a class also encapsulates things. So this is another way to see how you can organize the data better. Separating here for the graphical user interface, separating the layout from the actions. And there will be one function that will move the dot. Um, when we move the dot, we actually wipe the canvas clean. And that is an action that we will repeat over and over again while we are running animations. Here is the pattern again. Just again, to repeat it, we have a constructor in our class slide dot. The constructor determines the layout. Then we have one action. That action is already also called at the initialization. So when the GUI comes up, you will already see a dot drawn. But then that dot can move whenever the user slides the scale. So there is the static design in the class, and then the main event loop. So there's still a main program, but typically this main program only consists of the same three statements that we use in all of our GUIs. All right, so then the animation. So here you see the layout. We have again our canvas, but now I put it first row, first column. We want to control not the position, so the position is now moving at random, but we would like to move the stepping side, so everything is discrete here. We can draw continuous lines, but there actually are sequence of pixels. So the hopping is the step size, so you can imagine a frog hopping around in a pond. The steps that the dot makes is controlled by the vertical scale at the right. So here we will hop 10 pixels, but we can change that all the way to 100. But then also the speed is determined by the sleeping time. The sleeping time here is the time the dot or whatever the dot represents sleeps for a while before making the next hop. This translates into the refreshing rate of the canvas. So the computer will just wait a while, as or the while will be proportional to the number controlled by the horizontal scale. There are two buttons, and the buttons actually change the state of the animation. Starting starts it. So the GUI will just when it comes up in its default position. Dot is at the center with default values for the sleep time and the hopping, the step size. The start will set the state to true. A while loop will begin, and then the while loop will stop. So this is a while whenever the condition is true. That condition will be stopped when the stop button is pushed. Okay, so that's the plan. So when we define a GUI, we define the layout and we define the actions. So here I'm giving examples where I just show the layout and then I tell what the GUI looks like and what it does. On on a programming assignment or on any assignment, you will be asked to design the a GUI given a layout, and then also given uh, what the action should be doing. So you should define the methods. So there is this event driven again. It's all any changes that are set by the scale take immediate effect. So you can keep the animation running and make it go faster by decreasing the sleep time. And you can also increase the stepping side. So last time in the first half of this session, in the previous lecture, I showed the donut topology. Uh, we can here also use this to prevent whenever it hops with large step sizes, to actually prevent it from stepping out of its box. The GUI in any animation has a start and a stop button, but it has the main loop to perform the animation. So that's actually where the action happens. So the start and the stop button are there to clearly indicate what is done. So mainly to associate, uh, these are the two methods that are uh, clearly linked to the actions in the animation GUI. There's one data attribute, the size of the window, so you can make a small size or a large size, again expressed in pixels. All right, so the goal of this lecture and of any lecture is that you can start experimenting with the posted scripts. Please look at them, not only look at them, but run them. So with the exercises, I would try to make sure that you at least run them. So you can, instead of having, so when you did the project on the pie chart, you were most likely thinking in polar coordinates. So instead of having dot moving in a canvas, you can make your dot moving around in a circle. And you can make that dot go fast or slow, and also hop faster or slower. So that is exercise 3. Um, there is you can add a scale. So a scale can be used to determine also the precision. So with floating point numbers, we are using machine floats, and it doesn't really pay off to require more than 16 decimal places. Or perhaps you want to restrict the range between 1 and 8. If you think about monies, then it doesn't make sense to go past 2 decimals after the dot. So the first exercise asks you to add a scale to format the floats. We've seen the sliding puzzle. There was actually an animation there as well. So in some sense, I introduced the sliding puzzle very early in the first lecture on GUIs, mainly as a motivation. We can now go back to that sliding puzzle that also actually defines an animation. Um, so there were the scramble button and the unscramble, so you can adjust the speed of that animation. That essentially controls the refreshing rate of the clearing of canvas. Okay, I have prepared Jupyter Notebook. The Jupyter Notebook allows me to scroll through the code. Uh, it's not ideal for running the code, so typically the best way to run these scripts is still launching in a terminal window. Um, but I can still interlace markdown cells. So here is the first GUI, which introduces the scale widget. So when you think about the GUI, we think about the layout. So there will be the scale right horizontally in the first row. The second row will actually capture the value that is controlled by the scale. So we're going to control a floating point number that is stored and managed in this double var object. So double var is provided by the Tkinter framework. So we control the ranges, so the double will be between 0 and 1. Most likely it is a ratio. We determine the resolution, so no more than 3 decimal places. So that determines how the working precision of our number essentially. When we are displaying the scale, it wouldn't make sense to have ticks that are 1000 ticks there. That would not be helpful. So we have to define that the ticks are kind of spaced 0.2 from each other. So these are the things that we think about when we define a scale. We will use the entry widget as well. So that's why I'm also importing end and inserts. So here is the class definition. So the data attribute in the constructor. So we have the range, low and high. So they are defined as separate data attributes. They can already be used immediately. I could have put in the low and the high, but you see that I'm using the low and the high also to compute the tick interval. So I only want 5 ticks essentially, no matter what low and high are. And I'm also using this to define the resolution. So 3 decimal places divide by 1000. I can set the length, and then there is a command that associated and a variable associated. The variable is an instance of double. So then there is the positioning, 2 rows, 1 column. Okay, so then the action, what it does, it takes the value from the scale, and the show value here passes the value from the scale. So when you are associating a command to a scale, you actually pass it the value. So there is the double value. So I could also get, so there are actually two ways to get the value of a scale via this var attribute. So I could also get apply the get method to the var. But here I do this more directly by the argument of the command that is, or the method that is associated to the scale. So it is a double value. So when I place it inside the entry widget, so after deleting everything that is in there. So if you don't do this, then you will see often a garbled string coming up. So I will convert the value to its string representation and inserting that string in its entirety, value equals, then the value, I will insert that into the entry widget. So the code is in a script. So here is the script. So the script is not that long, not that much longer than 50 lines. So just exactly 50 lines. But you can see already the standard template of the layout. So let me run it. So you see here, what pops up is this scale. When I click on it, oops, when I click on it, I can move it. And you see instantaneously the value changes, and it goes all very quick. So the computer is quite apt at adjusting the values. So you see, even though the ticks are separated 0.2, the resolution is actually with 3 decimal places. So this is a very good illustration. If you have numerical parameters in a scientific simulation, you can set the values. And if you're calculation is not that sensitive towards changes in the input, then actually it doesn't, you don't need to rerun it if the input numbers are not more than, say, um, the resolution apart from each other. So that is also the rationale. Okay, this was our first GUI, a little bit boring, but let's go to the moving dot and the canvas again. So we want to visualize the canvas coordinates. In the previous lecture, we introduced the map. Whatever we wanted to graph, that was mapped into the pixel coordinates. So the canvas will be placed in a window. On top of them, there will be a horizontal scale for the second coordinate, um, the where the to the left or the right the dot will be, and at the right of the canvas will be the other scale for the other coordinate. So we will display the dot. In some sense, this is in preparation for the animation. So here is the class. So we have the constructor, which is a little bit more crowded because we have two scales, so it's a little bit repetitive. We have the horizontal scale, the vertical scale. We know how to set the resolution and the tick interval. So now actually 2 decimal places is more than enough, essentially. So there are the attributes. So there is no variable, well, there are two variables actually associated, two integer variables for the row and the column. So the x pos and the y pos, so this x position and the y position. So we didn't store this as a separate tuple, but this tuple is actually stored and managed. So it's stored in the objects that are instances of the class int var. Okay, so we will have a red dot. So you see the setting of the values. So there is the command. There's one single command that is the drawing of the dot. So that's over here. The dot will be placed right in the middle. And the drawing of the dot will most likely be executed as soon as the GUI comes up. As a consequence of this setting of the default value. So what does the draw dot do? So the canvas makes an oval, but the oval is stacked. So the oval is stacked with a dot. So it actually means that you give your object, when you make your oval, you give it a label, a tag, and because we don't want to see all the, so if you don't do the delete here, then the dot, whenever you move the dot, the old dot will still be there. So we will actually make a drawing. So that could be an intended consequence of your GUI, but here in preparation of the animation, the dot will be each time deleted. The other object that is being created is a text. So on top of the dot, should just higher, and note here I'm subtracting 10 pixel positions. So the y-axis goes downwards. So if you want to go up, you have to subtract from your y coordinates, which is kind of counterintuitive. But the draw dot is aware of the canvas coordinates. So here is the GUI. So you see, when it was the GUI coming up, I have my default position by the set method, and then I can shift around. So the nice thing here is that this also represents valid parameter range. So the dot can only exist on canvas. The highest I can go is 400 for both coordinates, and you see that There the dot is stuck at the right most top bottom most corner of the canvas. So this gives you a feeling of the canvas coordinates where they are controlled with the two scales. The code is not very long and not very complicated, and we do a lot of repetition here. So I'm giving longer codes, but I repeat them all the time. Um, Adding features or illustrating other issues. So here is the red, green, blue color wheel. So we can define colors by combinations. So we have 2 to the power 8 choices for red intensities. Most likely there might be more, but even already here, 2 to the power 8 times 2 to the power 8 is 2 to the power 16. We have 2 to the power 24. So 2 to the power 20, we are used to reasoning in binary, is actually a million. So we can make millions of colors. So actually 2 to the power 24 to be precise. 2 to the power 4 is 120. No, 2 to the power 4 is 16. So we can make 16 million different colors. All right, so let's look at this. So the show colors is the method, and then we have the constructor, so it all fits just on this coding cell here. Again, this is in some sense bad educational practice. So you are here now confronted with a complete example. If you do this in practice, start with a label. So the label is all the way placed on top, and perhaps place the canvas and then run it. So you have 5 lines in your constructor. You have your main, and that is it. So please execute early and often. So we have the canvas that we place row 1, column 1. Then we have the labels that kind of document what the scales are doing. So we have 3 scales. So I showed the code for the red scale on the slides already. And then it's just repetition. So you can, if you like, you can copy and paste. So you have 2 vertical scales, the red and the blue. And then you have the horizontal scale right at the bottom. We have the default values, so the intensities are 0.5, so these are the ratios. Setting everything 0 will make for black. Everything to 1 will make it white. So you can see the values. We have the variables green, red, and blue. They are intensity ratios, so they are doubles. We have the single command show colors. So whenever one of the scales is touched, the command show colors is executed. When it is touched and when you move for one of the 256. So then what does the show colors do? So this could be useful if whenever you want to define your own favorite color. So what we do is that we get the values of the scales. So here the show colors has a value, but it's only the value of the current scale. So here you see the limitation. You may have wondered with the previous GUI, with the sliding of the dot, why do you have a separate value and then the value also as the argument of the method? Well, here is a good example. So I'm getting the intensities, red, green, and blue, from the scales themselves. So I'm getting these floating point values. So they are ratios, so they are multiplied with 255, so scaled between the interval 0, 255, converted to the integer value, and then transformed in the hexadecimal format. So I'm not using the formatting strings, but I hope you can translate this into a formatting string using the percent operator. And here I have the formatting string. So the color string is defined by this symbol, and then the hexadecimal representations for the numerical values. So we are familiar with not only the binary but the hexadecimal. 2 to the power 8, 8 bits. So 2 hexadecimal characters will suffice to denote every intensity. And we will have 16 million different colors. So every time when the user touches the scale, so there is a print happening also here. So if you have selected your favorite color, you can see the red, green, blue intensity. I should also have, you could also have you could also display the color encoding. So the color encoding is recognized by the canvas. So there is the full color. I have this big rectangle, so I'm creating a rectangle. The rectangle is tagged, so it has the name box. So right before I'm going to create a new rectangle, I'm going to wipe out the old one. And I'm computing the coordinates of the middle, and you see it is positioned at the middle, and it is actually, so the rectangle is defined by the coordinates of the top. So the middle minus the middle is minus the middle is 0, 0. Here plus the middle is actually going to the other end. So I wanted to illustrate also the create a rectangle, which was used in the mouse draw application, something that we flashed up earlier. So this is another proper introduction of the methods that you can apply to a canvas widget. Okay, let's now look at this GUI. So you see the default value is just a dull gray. So if you mix all of the colors in the same intensity, you have some kind of a gray intensity. So let's make the red redder. So let's make this redder. So let's remove the green, and also let's remove the blue. So now we have the reddest red. So you can see what happens inside. So we have all kinds of pastel colors now. If I make it more green, make it more blue, and make it more red, then you end up with white. If you toggle everything off, so you have the bluest of blues, and then you go back to black. So just an intuition of how the colors work. What you see in the meantime, so here you see all the times that I ran this. So in the output of the GUI are actually all the values, me ending with 0, 0. Okay, so that's the next to last GUI. So I still have now about 10 minutes to introduce animations. So let's look at a random walk. So we have already seen the framework. So in some sense, to start an animation, there is a lot of code that needs to be set up, but a lot of code is repetitive. So here you see, if you look at the start of the constructor, you do have the definition of the canvas again, and you have the scales that will control the speed and the step size. And then there are two buttons that essentially start the animation and stop the animation. So the constructor defines the data attributes, the canvas, the scales, the labels, and then there are also the variables. The important variable is here, where I am now with my cursor, the to go. The to go determines the status. Is the animation going, or if if it's not. So it's a on or off state. So that's the important data attribute now in the animation. When the stop button is pressed, so where do we have the stop button? So I called it BT1, but the text actually says that there is a stop on this. So the command that corresponds to this is setting the state end of the animation to false. So that's actually an easy method. For symmetry, there is the start button. So I could have the animate there as well, but you see the start sets the animate to true and then launches the animation loop. So what does the animation loop do? It takes the current values, the position. So these are VXP, VYP are the local variables within this method. So this is used to determine the position of the moving dot. So you see each time we get the step size and we do a step backwards and or forward, so choosing a random number inside the range. So it's not always it's a random walk. So it is picking the next step in the X direction and the Y direction. So the previous moving dot, we had the two scales, and you could indeed see that there was a vertical and a horizontal movement. Now it appears that the dot is actually also stepping diagonally or in any direction. There is the donut topology. So whenever we risk falling off the canvas, we will adjust the position. There is the creation of the oval that takes the coordinates. And before we make the oval, we always wipe out the previous oval. So we always use consistently dot for the name. Sky blue too was kind of the color I first jumped on. There is the delay. So there is the scale sleep. So self dot sleep. So there is the self dot step. So there are the two scales, step and sleep. So you see the immediacy. So if, for example, the um, oval is being drawn here, for the next oval, we already checking the value of the step. And then we will draw the next oval in the update. So in the update here, but the after will sleep. So that's a method of the canvas. So that's one way to regulate the speed of the update. So the GUI will almost instantaneously go slower if the value for that is associated to the sleep is increased. Okay, so animations all can follow the same template, the same pattern. So let's run this. So I executed this already. So this is my last command. So here you see the GUI. So nothing actually comes up. I haven't pressed anything yet. So if I press the start button, the dot will start to move around. If I press the stop button, the dot will stop. If I press start, then the dot will start moving again. I can make it move faster, and I can also make it move more agitated. So you see actually it appears that it is a dot that tries to escape, that bumps against the walls. So in a later animation, I may show how billiards are working. So there is the same donut topology that is applied to simulate the movement of a moving ball on a billiard table. So there is the immediacy. So I shorten the steps. And I can also make the moving dot go extremely slow. So this illustrates a random walk. So now it's more like a walk when the step size is small. And you see the donut topology. So when the dot uh, moves too far down, it comes back up. Okay, I hope that these are already playful programs, that you have an incentive to run these programs. The way that I'm running them here is actually not entirely how you should be running them. So let me illustrate in the Jupyter Lab environment. So in the launcher, there is a terminal button. So there are my Python scripts in the current folder. So if I do Python move dot, so that will bring up the animation. And then I move the mouse into that animation and then I activate it. Uh, that to indicate that you can always interrupt it. So you can always interrupt it at the terminal window. If I type in Control C here, that will also interrupt the GUI. This is useful if somehow you have lost your window for some reason. But other than that, the animation doesn't stop here. It stops when, or the whole program stops when you close the window. Okay. So I hope that this was not too confusing. So Python and its Tkinter framework are very extensive, so one can teach an entire course introducing all kinds of features and all kinds of programming. And I hope that this introduction already shows the basic principles and also, again, gives the appreciation for object-oriented programming. So these are already very complicated programs, but with relatively little code in Python, we can prototype an application such as this.